This lab on pendulums is a pretty straightforward lab. I just want to make sure everything's going okay. This setup is designed so that this V shape of the string keeps everything swinging in a straight plane. Otherwise the pendulum tends to twist and spin and you don't get very good data. Now, pre-lab questions. There are three things that we can change about a pendulum. You can, if we look at a pendulum as an object that swings from a rope, okay, this thing right here at the end, this is called the bob, okay, and it's where all the mass is located. Now you can pull it up into the right or up into the left and it's going to swing through this distance. The bigger you pull it, the further you pull it from its equilibrium position, its rest position in the middle, the higher the amplitude. So amplitude is referring to this distance, and you can measure that with the angle. The bigger the angle, the higher the amplitude. Okay? So for each variable, describe what you think its effect on the period of the pendulum. Okay, so a lot of people in my class today said, well, if you pull it back further, it's going to have to swing through a greater distance, so that's going to take longer. So they thought maybe a higher amplitude means more time. Okay, and remember, period is the time for one complete oscillation, one complete back and forth motion, and so one complete oscillation is all the way over and all the way back. Okay, so they thought maybe if they had higher amplitude it would be more than if it just had to swing back and forth in this little spot. Okay. Length, kind of a similar argument I heard. And mass, a lot of people said, well, mass, it made this spring go slower, so it ought to make the pendulum go slower. Okay, so depends on what your thoughts are there. These are just what you think. We're going to test them to see what happens. Okay. Now, probably the most important step on here is setting up the LabQuest. Okay, make sure you put the mode to pendulum timing. Okay, with the LabQuest, what the photo gate on a pendulum does is it just starts and stops time. It's a beam of light that shoots from one side to the other, and every time that beam gets broken, it knows to start or stop time. But it's got to know that it's a pendulum that's going through there, or it will start and stop time incorrectly. Okay, and here's what I mean. If you have a pendulum swinging through the center point, it starts up here and it swings through. So as it comes through the pendulum, as it comes through the photo gate once, it gets an event. It gets blocked all of a sudden. Okay, it swings up to here and it swings back. Now it's gone through twice. There's another blocked event. And then it comes up here and then it comes all the way back and there's another blocked event. What's actually the time it wants? Well, since the time it wants is the time for one complete motion, it's not here and back again. It's here, back again, and back again. So it's the time for all three. So it has to start and stop every other time, not every time. Anyways, as long as you did that, it'll be okay. And then hold the mass off the center, measure a whole bunch of stuff. Cool. Okay. Now, your data here is your data here. Okay. I don't know what it is. I don't know how long your pendulum is. I don't know what all the different things is that you guys were doing. But what I want you to do when you're done is sketch the graphs of period versus amplitude, length, and mass. Don't know what that L is all about. Okay, in the space provided. Now it's just a sketch, so it doesn't have to be perfect. Okay, period is over here. Period, remember, is time in seconds, and that's true for all of these. So you'll have period, seconds, period in seconds, and then down here is amplitude, or length, or mass. Okay, and then it's just a sketch. So I don't know, I had a lot of these that were between 1 and 2 seconds, whatever. It doesn't have to be perfect. I just want you to have trend lines there so you can see what's happening. Okay, which variables appear to affect the period of the pendulum? There should only be one. Okay, of all of these three things, the only one that really I expect to affect anything is the length one. This does. Okay. Simple harmonic motion depends on restoring force to pull an object back into equilibrium, right? When it's on a spring, we rely on the spring. The spring pulls up to keep everything in motion. Okay. What about for a pendulum? Well, the pendulum gets pulled this way. What pulls it back down? Gravity pulls it back down. Okay. Recall, the period of a mass oscillating on the spring is given by this equation, T equals 2 pi m over k. What would be an analogous equation for the period of a pendulum? Well, if we think about this, T equals 2 pi, that we don't want to change, that's the angular part of it, whatever, it's still a sine wave, okay? Square root, okay, mass, it turns out it didn't matter. Okay, mass with the spring was this inertial thing that it resisted its motion. Here, we didn't really get the mass mattering so much, but we did get the length, right? And it's sort of a common relationship. On the spring, as mass increased, period decreased, or mass increased, period increased. Sorry. Length, as the length goes up, okay, the pendulum gets longer. The period also gets longer, so it's analogous to mass. And then K, the spring constant, that's what's causing our restoring force. Well, for us, it's gravity. Okay, so we should get the equation, the period equals 2 pi times length divided by gravity. It says use this equation to calculate the period of each pendulum above. So I actually want to see just an example calculation, and maybe you don't know the length, but hopefully you know the length for this one. And these ones you don't have to calculate every single one. Maybe just see one and see how it compares. And part 3 mass, calculate one, see how it compares. They should be fairly close. But the cool thing is you can use your equation and your data to calculate a value for g, because you have the period, you know 2 pi is a constant, square root of L, if you use your length ones, divided by g, and you can solve this for g. To do that, right, you're going to take t divided by 2 pi squared equals L over g. So if I want g, I've got to go ahead and multiply both sides by g, and g equals length divided by t squared over 4 pi squared. Okay? Now I just distributed my square onto that. If you think about what that means, that's invert and multiply, so this is length times 4 pi squared divided by t squared. Okay? And this is an interesting equation. G should be in meters per second, and so length is meters, t is time, but it's squared, so per second squared, and then this 4 pi squared, this is just our multiplicative factor. This is just telling us, basically it's converting from angular to linear. Okay? Alright, good luck. Hopefully you get this done, and then there will be a couple problems out of the book on pendulums.